Hello and welcome to this GCSE Chemistry exam paper walkthrough where I'm going to take a look at the 2022 Paper 2 by the AQA exam board. Download the questions from the link in the description, and throughout I'll be modelling my thoughts about the questions in red, and the answers that will get you the marks will be written in purple. This question is about copper wire and copper compounds. Copper is used to make electrical wires, and then the diagram shows how electrical wires are insulated using an addition polymer called polybutene. And you can see this is a dark grey on the diagram, and the copper wire runs through on the inside of this, and they've taken the polybutene off some of the copper wire just so you can see that there is copper wire on the inside. And then for part A, we're shown the addition polymer polybutene. We're shown its structural formula. And that's a formula where you don't show every single bond that there is, but you can work out how the atoms are arranged from the structural formula. And you can see that there are some features of the polymer that are common to all polymers. First of all, you have something inside some rounded brackets, and this is referred to as the repeating unit of the polymer. And that's the bit that repeats again and again and again. How many times? Well, n times, where n is a huge number, hundreds, thousands maybe, of this repeat unit. And all of the atoms within the polymer are held together by these things shown as sticks. These are covalent bonds. And then on the outside, we've got these bonds, and these are referred to as trailing bonds, and they symbolize the fact that the polymer chain grows and grows and grows in each direction. And then we're told that the polybutene is produced from the monomer butene, and we're shown a partial diagram in the figure below, and we're asked to complete this diagram to show the displayed structural formula of butene. In other words, the monomer that this polymer is produced from. And so the first thing to note is that when you are doing addition polymerization, we are using monomers that are alkenes. And the very first thing that we need to do then is show the characteristic double carbon-to-carbon bond that is found in all alkenes. And when you're showing this for polymerization, the double carbon-to-carbon bond is always between the two carbon atoms that are going to form the spine of the polymer chain. And so in other words, these two carbon atoms here, they have a single bond once the polymer has formed, but that polymer forms because the double bond that is in the monomer breaks open partially and becomes a single bond. And then another feature of the monomer is, in fact, that all of the atoms inside the polymer repeat unit are present inside the monomer, and they're bonded in exactly the same way. So we need the bonds between the carbons and the hydrogens, and the CH3s and the carbons above and below our double bond. And the final two features of the polymer, the brackets with the N and then the trailing bonds, they aren't included in the monomer diagram. You could probably get away with the brackets and the N, but you certainly couldn't get away with the trailing bonds. The trailing bonds are only present in the polymer. And so the monomer has a double bond, and that is the feature that breaks open to make the single bond and allow that polymer chain to grow. And then we're told that copper can be recycled using scrap copper wire. And then we're asked to suggest why polybutene insulation needs to be removed from scrap copper wire before copper is recycled. Now, when you're shown a suggest question, that means you haven't been explicitly taught the answer to this question, but you need to be able to work out the answer using your knowledge of chemistry that you can bring to this question. And normally for a suggest question, there are a huge range of possible answers, and I will list a few of them. First and foremost, we need to recognize that during the recycling process, you take the thing that you're going to be recycling and you heat it up and you melt it, and then you set it into new shapes perhaps. And if we were to do this with the insulated copper wire, then the copper would be mixed in with the polybutene, or we could say it would be impure. And having this polymer mixed in with our metal is almost certain that the properties of the copper, for instance its conductivity, are likely to be negatively affected. It probably wouldn't conduct electricity very well. Other things you could say are problems that might occur during the recycling process, which is that the polymer might be flammable and therefore it might burn during the process, and this could in fact produce toxic fumes. And in fact, we don't even know if polybutene is a type of polymer that is recyclable. We haven't been given that information in the question because not all plastics will melt at all. Thermosetting plastics will not. Describe how scrap copper wire can be recycled to make new copper water pipes. Well, there's two parts to the process of recycling. You need to take your old material and you need to heat it until it melts. Having done that, we will have a molten copper situation, and this molten copper needs to be recast into the shape that we want, so into the shape of the pipes. You could probably say the word reformed or remolded instead. The key ideas there are the copper is melted and then it is formed into the new shape of the pipes. Suggest 2 reasons why recycling scrap copper is more sustainable than extracting copper from copper ores. There's 2 things to note before we think about the actual answer here. First of all, we've been asked to suggest, and that means that we don't directly know the answer. And secondly, the question uses a comparative word, more. So this is asking why it is more sustainable. So any answers that you give must be comparative. I think the thing that's worth mentioning first here is that copper ores are a finite or non-renewable resource, and therefore we need to talk about the fact that recycling the scrap copper is going to conserve these copper ores and therefore make them last longer. And then secondly, the act of recycling means that we don't need to extract more copper from the ores, and therefore less energy resources will be used to recycle copper than to extract it from the ores. Additionally, if we aren't recycling copper, then we're sending the copper waste to a landfill. And so if we recycle copper, therefore, there will be less landfill use or less waste. We could also talk about a specific environmental impact that is avoided by recycling. So, for instance, since we use a lot of energy to extract copper from its ores, this energy will come from burning fossil fuels, which will produce carbon dioxide, which will have an impact on global warming. And so, therefore, recycling copper indirectly has less of an impact on global warming because of this reduced carbon dioxide production. Copper sulfate is a compound of copper. Copper sulfate solution contains copper 2 ions and sulfate ions. A solution is added to copper sulfate solution to show the presence of copper 2 ions. Name the solution added and give the result of the test. Well, this type of reaction is called a precipitation reaction. The ions that are present in copper sulfate are dissolved at the beginning, they are aqueous, and then we add something to that solution which results in an insoluble solid forming, and that insoluble solid is a precipitate. And we've been asked to name the solution that we should add here, and so that means that a formula by itself will not be acceptable. And so the substance that gives a result that shows the presence of copper 2 is sodium hydroxide. What happens is the hydroxide ions from the sodium hydroxide react with the copper ions from the copper sulfate, and we make copper hydroxide. And copper hydroxide is an insoluble solid called a precipitate, and it is blue. And so the result that we would need to share here is that this is a blue precipitate. And unfortunately for questions like this, you need to get the name of the solution correct in order to get the credit for the result that you would observe. So it's really, really important that you remember the names of the chemicals that you add to test for each of the ions. And then we're asked to describe one test to show the presence of sulfate ions in copper sulfate solution and give the result of the test. So this is effectively the same thing here, except that they haven't really directly asked us to name the chemicals, but effectively it's the same thing. Because when we're testing for sulfates, we need to know that sulfate ions react with another type of ion to make a new precipitate. And the ion in question is the barium ions, because what happens is the barium ions react with the sulfate ions to make barium sulfate. But just like in the previous question, you're not allowed to say barium ions because you can't get a bottle of simply barium ions. What you would get is you would get a solution of barium chloride. And this barium chloride is normally acidified. But I don't think that's necessary here because this is only a 2-mark question. And so in other circumstances, you might expect to say barium chloride solution and hydrochloric acid for 2 marks, and then the result is that you would see a white precipitate. Again, you need to have the test to match the results. If you give the wrong test but the correct result, you won't get the mark here. And whilst that seems harsh, it's actually reasonable because quite a lot of the precipitates that you observe in GCSE chemistry are white, and so if in doubt, it probably is a white precipitate, but you need to get the correct chemical test that would give that result. A student investigated the change in mass when hydrated cobalt chloride was heated. The word equation for the reaction is shown below. We've got hydrated cobalt chloride on the left-hand side, and then we've got this symbol in the middle, which is the reversible reaction symbol, and we make anhydrous cobalt chloride, and we've got water. And so hydrated cobalt chloride means that there is water in amongst the crystals of cobalt chloride, whereas anhydrous cobalt chloride means that all of that water has been removed. And then we're shown a method for how this reaction is carried out. If you find method questions difficult, I suggest that you draw diagrams to help you track what is happening. The diagrams don't need to be amazing, they're not going to get you marks necessarily, but they'll help you understand what's happening when it comes round to answering the questions. And so first of all, we add 2 grams of hydrated cobalt chloride to an empty test tube. We measure the mass of that test tube and its contents. And then we heat the tube gently for 30 seconds, allow it to cool, measure the mass of the tube and the contents again, and repeat those steps until the mass of the tube and the contents no longer changes. And we're shown a table of results for somebody's experiment. You can see that the heating time is in the first column. That's effectively the independent variable. That always goes in the first column. This is measured in seconds. And we're shown that the mass of the tube and contents is in grams. And we're tracking this for 5 separate readings. Our first command is to determine the mass of the empty test tube. Well, we need to do 2 things here. First of all, we need to remember that we used 2 grams of the hydrated cobalt chloride for the empty test tube. And at the beginning, before any heating had occurred, the test tube and its contents had a mass of 26.5 grams. And so we just need to simply subtract 2 from 26.5, and that gets us 24.5 grams. And then we need to explain why the mass of the test tube and its contents decreased as time passed. In other words, as we heated it. Well, there's 2 marks for this question, so we can't just simply say one thing. The first thing that we should say, though, is that we're producing water vapour. There was water inside the hydrated cobalt chloride, and that water will have left those crystals, and it will have been produced as a gas. And then obviously, once you produce some gas, that gas will escape from the tube if it's not sealed. And it doesn't mention anything about sealing it. And in fact, it would be very dangerous to seal it. And so we're saying that water vapour is produced. And so that water will then escape as the vapour does. And so the mass of that water was not measured because it was no longer in the tube. And then the final question about this experiment says, suggest why the tube and the contents were heated until the mass does not change. So you can see in the table that after 30 seconds, the mass had dropped by 0.3 grams, and then another 0.3 grams, and then another 0.3 grams every 30 seconds. But then between the 90th and the 120th second, that mass doesn't change. What that allows us to do is that allows us to be confident that all the hydrated copper chloride had evaporated, or in other words, all the water from the hydrated copper chloride had evaporated, and any reaction that was occurring has now ended, and no more water will have been produced. Energy is taken in from the surroundings when hydrated cobalt chloride is heated. When 238 grams of hydrated cobalt chloride is heated until the mass does not change, 88.1 kilojoules of energy is taken in. The students in our experiment heated 2 grams of hydrated cobalt chloride until the mass didn't change. Calculate the energy taken in during this reaction and give your answer to 3 significant figures. The first part of this question requires us to work with proportionality. If 238 grams of hydrated cobalt chloride takes in 88.1, 2 grams will take in much less. And so there's a few different ways that you could approach this. First of all, you could simply leave this as a fraction. 2 is obviously a lot smaller than 238. How many times smaller? Well, 2 divided by 238 is it expressed as a fraction. And then what we would do is multiply this fraction by 88.1 kilojoules, and that will get us our answer of 0.740336 kilojoules taken in. Alternatively, if you're not comfortable with fractions, what you can do is you could work out how much energy is taken in per gram of hydrated cobalt chloride. And so to do that, what you would do is you would take 238 and divide it by 238, and that would of course be 1. And then if you take 88.1 and divide that by 238, we get 0.370168 kilojoules. And so that's how many kilojoules are taken in per gram of the hydrated cobalt chloride. And so when we double this, because we're interested in 2 grams, we get 0.740336, which understandably is going to be the same number. So whichever of those two methods you prefer, we have arrived at our almost final answer of 0.740336. Now, we've been commanded to report this to 3 significant figures. And so when you're dealing with a decimal that has got 0 at the beginning, we need to remember that that 0 does not count as a significant figure. The first significant figure is the first non-zero value. So in other words, the 7. And so we need to take away everything after the 0.740. We check that the number after the 0 is less than 5, which it is, it's a 3, and so that rounds down rather than up. And so our answer here is 0.740. Depending on how you've rounded it up, you are likely to have a little bit of leeway either side of this answer. And then the final question says, what type of reaction is taking place when the hydrated cobalt chloride is heated? Well, heating is providing thermal energy for the reaction to occur. That energy is going into the chemicals, and so the chemicals will have more energy after the reaction has occurred than before the reaction. And so this is simply referred to as an endothermic reaction. Alternatively, we could recognize that the hydrated cobalt chloride is falling apart. We start with 1 reactant and we end up with 2. So we could instead refer to this as a decomposition reaction. And it's a decomposition reaction that requires heat energy. So it is a thermal decomposition reaction. We could also remark on the fact that there was the reversible reaction symbol in the equation that we were given. And so instead of these 2 possibilities, we could instead say this is simply a reversible reaction. My preference would go towards referring to it as being endothermic because heat energy is going into those chemicals, and therefore this is going to be giving the chemicals more energy than they started with, which is what an endothermic reaction is. This question is about life cycle assessments, and we're told that milk bottles can be made from either glass or from polymers. And we are shown a lot of information in this table about the impacts of these 2 different possible sources of our milk bottles on the environment. And our command is to evaluate the use of glass for milk bottles compared to polymers. And we're using features of the life cycle assessment that we've been given, and we're commanded to use the table above. This is a really, really common type of question. It's normally 6 marks, as it is here. Sometimes it might be 4 when they give you less data to consider. And I've got 3 really important tips to help guide you in this type of question. And the first one, when you're commanded to do an evaluation, you need to make a judgment, or you need to come up with a conclusion. And that conclusion needs to be which of these types of milk bottle is more sustainable, which one has got the least impact on the environment, because that's what life cycle assessments are about. They evaluate the environmental impact of a product across all of the stages of that product's life, and these stages are shown on the left-hand side here. And so the only thing that we're allowed to bring into this question, into our answer, is how is the environment affected by these things that we're told. So that's the first thing that I would say to you. Make sure you make a conclusion, and to help you to make that conclusion, I would say make the conclusion at the very beginning. Start with your conclusion. How will you know what your conclusion is before you've written the rest of your answer? Well, then comes my second tip. To help you decide what your conclusion is going to be, I recommend that you consider each of these things in turn before you start to write anything, and you make a decision as you read it about which of these things is worse for the environment and which is more sustainable. So let's do that now. The raw materials for glass and for polymers. Well, the raw material for polymers is crude oil, and we know that crude oil is finite, and that therefore makes it worse than glass, which uses sand and limestone, which are, whilst they take a long time to form, they don't take millions of years to form. And so I recommend putting smiley faces and sad faces in each of these instances. The energy needed to produce the raw materials, 6,750, that's more energy than 1,710. So the glass has got a sad face, the polymer a happy face. The energy needed to manufacture the bottle, well, the glass again has more energy requirements and the polymer has less. The mass of the bottle in grams, it's not obvious why that matters, but the fact that the glass is heavier is definitely worse for the environment because that will impact on the energy resources needed to transport the bottles. The mean number of times this can be used, well, the glass wins this contest because the glass can be used 25 times compared to the polymers only once. And then the disposal method at the end of the life, we can recycle the glass bottle to make different products, and we can recycle the polymers. And so since they can both be recycled, this is probably a draw. And so now we've done our brief survey of the data, you can make your own decision about which of these you think should win. You could be just incredibly quantitative about this and refer to the fact that the glass has got 2 smiley faces and the polymer has got 3 smiley faces. And so the polymer seems better. Don't spend ages deciding on how you're going to phrase this. You need to just give a reasoned discussion, and that's all that matters. And so you can argue either side of the case here. And then my next tip is that when you are writing your answer, you need to support your answer. So what I mean by that is don't just quote things from the table and expect to get all the marks. You're likely to actually only get 2 marks out of the 6 here if you simply quote things from the table. You need to make comparisons between the information and you need to explain why those comparisons matter. And so the final thing that I would say, this is not so much of a tip, but more a advice about how much you actually need to write. If you make 4 comparisons and you explain the impact of each of these comparisons in support of your judgment, that will be plenty. It's not 6 supported arguments for 6 marks. This is quite a hard question for the examiner to answer, but from your point of view, you just need to develop 4 points. And I'll see how many points I can fit into my development here. So I'm going to make a decision that the polymer is the best, just because we need to make a decision and it doesn't really matter what I pick. And I'm picking it because it's got more smiley faces. And so you begin with your judgment, and your judgment should say that overall, I think that polymer is the best choice for the milk bottle because it has the least impact on the environment. And then we need to support this statement. So let's start with the positives, the reasons why I chose the polymer. First of all, the polymer uses much less energy to process the raw materials. And why is this an advantage? Well, if it requires less energy, then that means it will use less energy resources, and the energy resources come from fossil fuels. And we know that burning fossil fuels will cause the release of carbon dioxide into the atmosphere, and that will have a negative impact on global warming. And so I can say that polymers have got less of an impact on global warming because they require less energy, not in fact only to process, but also to manufacture those raw materials. So I've supported my answer. I've not just quoted numbers, I've said more or less, and I've supported why that matters. We can also support our answer with numbers, and we don't need to do that every time. And so I'm going to show you the way that I could do it, and I'm just going to do it once. And so how many times less energy is needed to process the raw materials for the polymer? Well, if we divide 6,750 by 1,710, we find out it's 3.95 times less energy. And in fact, if we do 750 divided by 90, that's 8.33 times less energy. And so either of those bits of data would support it. But let me repeat, you don't need to fire all the numbers into this. But if you did do that, it is much better to use your comparative numbers than to just lift numbers from the table. And if we take a look at the mass of the bottle, we can say that the polymer is much lighter. Don't just quote the masses, say it's much lighter. And in fact, we can show off and say it is 10 times lighter. And if it's 10 times lighter, then that might mean it takes 10 times less energy to transport, which again is going to conserve our energy resources for everything that we've already said. And then we should maybe finish by saying, I still think polymers better, even though there are a few negatives, and let's list those. And the first negative is that the polymer uses crude oil. And we know that crude oil is a finite resource, will eventually run out, whereas glass has much more sustainable raw materials. And the other big negative of the polymer is it can only be used once during the lifetime of the bottle, whereas the glass can be reused. And this reuse of the glass bottle is going to conserve the natural resources required to make it. And so we won't need to use so many resources because we are reusing the bottle over the course of its lifetime. Although reuse is not without its cost, it does require energy and water to wash the glass bottles ready to make them to be used a second, third time, etc. And then we should talk about the disposal just very briefly, just acknowledge the fact that both of these can be recycled, and so energy will be required to melt and reshape these things, and so that's neither a pro nor a con in favour of one over the other, but we should recognise that recycling the polymer conserves those finite resources that we talked about, and so that means the fact we're using something that is finite, but then we're recycling it, you could say that that offsets some of the negativity of using finite resources in the first place. And so there's a lot going on in a question like this. And so let me repeat that to get the full marks, to get all 6 of these marks, you need to make a strong and definite judgment, which you are supporting using information from the table where you're making comparisons, at least 3, hopefully 4. And then you are supporting those comparisons with, why do these comparisons matter? What is it that is negative for the environment or more sustainable about what we are proposing? Milk is also sold in cardboard cartons, and a cardboard carton has got a volume of 40 cm cubed of cardboard used to make it, and then the density of cardboard, we're told, is 0.40 grams per cubic centimetre. And we've been asked to calculate the mass of this carton made from cardboard, and we've been given the density equation to do this. Now, there's 2 different ways of answering this question. The first way is if you're confident with rearranging, in terms of confident with the algebra, I would propose doing that. And what we need to do, therefore, is make mass the subject of this expression. And so to do that, we need to get mass on one side by itself, Currently, the mass is being divided by volume. So we need to multiply that by volume, and then what we'll get is mass multiplied by volume divided by volume. And the volumes cancel out to make 1, so it's technically mass multiplied by 1, but we'd never write the 1. But we should know that whatever we do to the right-hand side, we must also do to the left-hand side, and so we need to multiply that density by volume as well. And so we've got mass equals volume multiplied by density. And then we plug those numbers in. The volume is 40, the density is 0.40, and that answer is 16 grams. I said there's a second way to do this. If you're not a fan of algebra, my recommendation is once you've got your equation, substitute the numbers in, because it is much easier to rearrange an equation with the numbers in rather than with letters or words. And so what we have here is 0.40 for the density is equal to the mass, which we don't know, divided by the volume, which is 40. And so we do still need to rearrange this, but faced with mass divided by 40 is equal to 0.4, it's easier to see that, well, if we multiply that right-hand side by 40, we end up with 40 divided by 40, which we know is 1, and so that will kind of disappear from the right-hand side and cancel out. And if we're multiplying the right-hand side by 40, we need to multiply the left-hand side by 40. So 40 multiplied by 0.4 is the mass, which of course, again, will get us an answer of 16. This question is about the fractions obtained from crude oil. Crude oil is separated into fractions by fractional distillation. The fractions obtained from crude oil include lubricating oil, naphtha, and petroleum gases, and Table 1 shows the boiling point ranges of these fractions. Crude oil is a mixture of hydrocarbons, which are molecules made from only hydrogen and carbon. These hydrocarbons vary dramatically in length. The very long hydrocarbons have got a higher boiling point than the shorter hydrocarbons. And when we separate them out using fractional distillation, we don't separate them out entirely, we separate them out into groups of similar length hydrocarbons, which are referred to as fractions. And we can tell that it's not totally pure because the boiling points have got a range. And so we are asked to explain how these fractions are obtained from crude oil by fractional distillation. And there are 4 marks for this question, so we need to make sure we give a well-developed answer that refers to the fractions and the data in the table. The first step of fractional distillation is where the crude oil is introduced to a boiler. At this point, the crude oil is heated until it vaporizes. When it goes in, it's normally a liquid, and in this stage here, it turns from a liquid into a gas. And then the vapors move through and into this, which is called the fractionating column. It's a big tower with lots of different levels. Now, once it enters the tower, these vapors start to rise up the column. Now, this column is hotter at the bottom and colder at the top. So as the vapors move away from the bottom of the column, they will cool down. And when vapors cool down, they condense. And that means they'll turn back from a gas into a liquid. Now, the subtlety for this question here is it asks how these fractions are obtained from crude oil by fractional distillation. So we need to link it to these 3 named fractions. Now, since the vapors are going to condense as they rise up, we need to think about where they will condense. And they'll condense at the level of their boiling point. And the lubricating oil has got the highest boiling point. That means it needs to be hotter to keep lubricating oil as a vapor than it does for the other 2. And so the lubricating oil will condense first. That means it will condense lower down than the other 2, because if it's, say, 450 degrees C at the bottom, as it rises to here, it will condense and then it will come out at this stage at about 300 to 350 degrees C. The naphtha will condense next out of these 3 because its boiling point is the next lowest, and the petroleum gas will either condense at this level or possibly even not even condense at all because it will have the lowest point of all. And so the petroleum gases are actually unlikely to condense in this column. And so how do we make sure that we get all 4 of these marks? Well, first of all, we need to say that the crude oil is heated to make it vaporize or to make it evaporate. And then when it enters the fractionating column, it will rise up and it will cool down because it is cooler at the top than it is at the bottom. And then these vapors will condense at different levels. And we can be specific and say that the lubricating oil will condense lower down than naphtha. And they condense at these different levels because they have got different boiling points. The longer hydrocarbons have got higher boiling points, and that would be lubricating oil out of this trio of different fractions. And petroleum gases have the lowest boiling point of the 3, and that's because their hydrocarbon molecules must be smaller. You don't have to use all of these precise words that I've written down here, but there are a certain number of words that you really should try and include in an answer like this. For instance, you need to talk about the crude oil vaporizing or evaporating. You need to refer to the actual fractionating column or tower by name. And then you need to talk about the gases condensing, and you need to use the phrase different boiling points. If you want, you could support your answer with a diagram. That would mean that you would need to write less description because your diagram would cover some of the same details. Fractions from crude oil can be processed to produce feedstock for the petrochemical industry. Which 2 are useful materials produced from this feedstock? And that's what feedstock is. It goes into a second set of processes and the crude oil fractions get converted into new substances that have got new uses. And we're told that we need to tick 2 boxes, and that's because there are 2 marks up for grabs here. Now we need to remember that crude oil is a mixture of hydrocarbons, and these are covalent molecules containing only carbon and hydrogen atoms. And so alloys, the first answer, is definitely wrong because alloys are made from metals with other substances added in that might not be metals, but we definitely need metals for it to be an alloy. And ceramics, well, ceramics include things such as glass and clay and pottery. And so whilst that seems like it could maybe be reasonable, it isn't. You don't use crude oil to make pottery and glass. Detergents. This is one of the correct answers. Detergents are cleaning products, and that's one of the things that you can convert the fractions from crude oil into. Fertilizers. This is not the correct answer. Fertilizers are things that help plants to grow, help crops to grow, and you don't put crude oil or anything derived from crude oil directly onto fields. That wouldn't help the plants grow. The fertilizers need to contain things such as nitrogen and phosphorus and potassium to help those plants grow, not carbon and hydrogen that you get in hydrocarbons. And that means that the last answer, solvents, must be the second correct answer, and it is. Solvents are used to dissolve things, and the fractions of crude oil are really good at dissolving a certain type of substance, specifically substances that do not readily dissolve in water. So the correct answers are detergents and solvents. Another fraction obtained from crude oil is petrol. Petrol contains a hydrocarbon with the formula C9H20. Complete the equation for the complete combustion of C9H20, and you should balance the equation. Before we do this, we just need to clarify a few terms. A fraction is a group of hydrocarbons that have got similar lengths and similar boiling points, and a hydrocarbon, as you can see from this example here, is a compound containing carbon and hydrogen only. Now we're completing the equation for combustion. In combustion reactions, this is where substances react with oxygen. Oxygen supports the burning of substances, and therefore that means that this first gap needs to be acknowledging that it's oxygen that is required for combustion to occur. Now we're balancing this equation, which means that the word oxygen won't be enough. We need the formula of oxygen, which is O2. When you write this, you need to make clear that the oxygen is a capital letter. Try and make it the same height as the other letters, if not larger. And the 2 needs to be a subscript, sort of down on the line in this space here. So we're reacting our C9H20 with O2. And then they've taken the care to say that this is complete combustion, and the opposite being incomplete combustion. But during complete combustion, what happens is all of the elements in the substance will oxidize. That means they will react with oxygen. And so the carbon in the hydrocarbon will fully oxidize, and we will produce carbon dioxide. And that has got the formula capital C, capital O, and then a 2, because there are 2 oxygens but only 1 carbon. And so that needs to go into one of these spaces. It doesn't really matter which. And the hydrogen will oxidize to produce water, so H2O, again making sure those numbers are small subscript numbers down on the line and definitely well below halfway up your capital letter. If this was to be incomplete combustion, it would still make water in the exact same way with the same formula, but the carbon would not oxidize fully. We might make carbon monoxide or simply carbon particulate, so capital C. But we've got our equation now. If we did nothing else, we would get 1 mark. But we have been commanded to balance this equation. And balancing equations comes from the law of conservation of mass, which is that atoms cannot be created or destroyed. So however many atoms of each element we've got in the reactants, we need to have the same in the products. And so currently this is an unbalanced equation because all of the elements are wrong. We've got different numbers of all of them on either side of our arrow. And so my advice when you're balancing combustion equations is to leave the oxygen until last, because oxygen is in both of the product and one of the reactants, whereas each of the remaining elements is only in 1 molecule on each side of the equation. And that's a good tip generally, not just for combustion. Leave the element that appears the most in a balanced equation until the end. So it doesn't really matter whether you start with the carbon or the hydrogen. I'm going to start with the carbon because I wrote the CO2 first. I've got 9 carbon atoms in my hydrocarbon reactant, and I've only got 1 carbon atom in carbon dioxide. And so what we need to do to make this balanced is we need to add the multiplier of a 9 in front of the carbon dioxide. That gives me 9 carbon dioxide molecules. Each molecule has 1 carbon atom, and so 9 carbon dioxide molecules gives me 9 carbon atoms. And again, still leaving the oxygen alone. We'll get to that. And then the hydrogen, we've got 20 hydrogen in our reactant. We've got 2 hydrogen in each molecule of H2O. So therefore, if we had 10 molecules of H2O, that would be 10 lots of 2 hydrogen. And so that would give us 20 hydrogen. And so this is now balanced for hydrogen. And now we need to finish by balancing for the oxygen. And now what we know is what numbers are in front of the molecules in the products. We've just put this 10 in front of the H2O. There is 1 atom of oxygen per molecule of water, and we've got 10 molecules of water, so we've got 10 atoms of oxygen. And then there are 2 atoms of oxygen for every molecule of carbon dioxide. We've got 9 molecules of carbon dioxide, so that is 18 atoms of oxygen. So in total in our products then, we've got 18 plus 10, so that is 28 atoms of oxygen on our product side, on the right. Which means we need 28 atoms of oxygen in the reactants as well. Each O2 molecule has got 2 atoms of oxygen, so to get 28 atoms of oxygen, we need 14 O2 molecules. And so we need each of these numbers to get the second mark for this question. And then we're told that petrol obtained from crude oil contains sulfur impurities. And we've been asked to explain why sulfur impurities are removed before petrol is burned in car engines. Often when you've been asked to explain why we do something, it's quite useful to approach your answer from the point of view of, well, here's what would happen if we didn't do this thing. And that's what I recommend here, because if we don't remove the sulfur impurities before we burn the petrol, they will still be in the petrol when we burn it. and the sulfur impurities will burn along with the petrol. And remember that burning is a reaction with oxygen, so sulfur will react with the oxygen and will make an oxide of sulfur. And the most common oxide of sulfur is sulfur dioxide. And so that's the first mark here of the two that are available for this question. We produce sulfur dioxide. And then the second mark is for explaining why this is an issue. There's a couple of issues with sulfur dioxide. The main one is it causes acid rain. And so that's probably the one that I would recommend mentioning here. And we could say something else. We could say that it causes respiratory problems or breathing difficulties, or you could even specify a respiratory problem such as exacerbating asthma or bronchitis or something like that. But I suggest that you keep it simple by saying that it causes acid rain or it causes respiratory problems. Table 2 shows information about two more fractions obtained from crude oil. And so we've got kerosene and heavy fuel oil, and we're told how many carbon atoms are in a typical molecule of kerosene and fuel oil. The student predicted that heavy fuel oil is more viscous than kerosene. Viscous is sort of the opposite of runny. So if something is more viscous, it will be less runny. And we're told that the student's prediction was correct. And we've been asked to justify the student's prediction. So in other words, say why we think the student was correct to make the prediction, not why has it been found that they are correct. And so the first thing that we need to do is explain the general principle, the relationship between the number of carbon atoms in a molecule and viscosity. And so stating the general relationship is that as the molecular size increases, the viscosity increases. We could also say larger molecules or longer chains, or even just more carbon atoms. And so once we've stated that relationship, and that relationship goes beyond these two fractions that have been mentioned here, so we're talking about all the different hydrocarbon fractions that there are, this is the relationship. And then we use the question and say, right, well, given that this relationship is true and that heavy fuel oil has more carbon atoms than kerosene, or it has larger molecules than kerosene, that's why their prediction should be correct. And so the molecular size increases and viscosity increases, and heavy fuel oil has larger molecules. The heavy fuel oil fraction can be processed to produce smaller hydrocarbon molecules. Name the process which produces smaller hydrocarbon molecules from heavy fuel oil, and give the conditions for this process. Well, the process that they're asking us about here is called cracking, and we carry cracking out because the larger hydrocarbon molecules, for instance heavy fuel oil, are less useful to us. They don't burn so easily, and they are more viscous, and they have a higher boiling point. And so we carry out this cracking process to produce smaller hydrocarbon molecules that are more valuable to us, and they are more useful to us. And they're more useful for two reasons. First of all, the smaller hydrocarbon molecules generally are better fuels because they are more flammable and they are less viscous. But additionally, we can get other hydrocarbons produced as well called alkenes. To carry out the cracking process, there are two crucial conditions. Firstly, we need to use a high temperature. And it's really important that you say high temperature. You don't say hot or heat or something like that. It needs to be high temperature. I would probably avoid mentioning a specific temperature, just in case you say something that is slightly wrong or slightly outside the range that they will accept. And so high temperature is absolutely fine. You don't need to worry about the specifics. And then the second condition is that you need to use a catalyst. The catalyst that is typically used is a zeolite catalyst, but if you are worried that you might not remember that name, you can just simply say a catalyst. It's far better to just say catalyst without saying the wrong catalyst. And this catalyst allows the reaction to happen at a higher rate, and the catalyst itself is not used up. And so that means that we get the increased rate of reaction that allows us to make more product without dramatically increasing our costs. And so we've got 3 marks for the whole question, 1 for the name of the process and 1 for each of the conditions. Hydrocarbon molecules containing 7 and 8 carbon atoms can be produced when heavy fuel oil is processed. Which pair of hydrocarbon molecules would both turn bromine water colourless? Well, there's two things that we need to understand before we make our choice. First of all, the turning of bromine water colourless. That is a test for unsaturation. And so bromine water reacts with alkenes. Bromine water is a sort of a yellowy colour, and it goes colourless when it is in the presence of an alkene. So we're looking for two chemicals that are both alkenes. And the hydrocarbons that are alkenes have got the general formula CnH2n. In other words, the number of hydrogen atoms in the hydrocarbon has to be double the number of carbon atoms in the hydrocarbon. And so for our hydrocarbon that has got 7 carbon atoms in, we need to double that 7 to get 14 hydrogen atoms. And that allows us to rule out the bottom 2 because C7H16, that's an alkane's general formula, not an alkene. And then for the hydrocarbon that has got 8 carbon atoms in, doubling 8 gets us 16. And so that means that our top answer is the correct answer, and the second one down is incorrect because C8H18 is an alkane again. And so the top answer is correct because we have got 2 alkenes. This question is about water. Sewage is wastewater, and sewage contains organic matter. Describe how sewage is treated to remove organic matter. And we've got 4 marks for this question. Well, sewage generally is a name for anything really that enters into our sewers. And so that's water from when you flush your toilet and when it goes down the drain, when it comes from agricultural systems, so runoff from fields and chemicals and fertilizers that might have been used in industry, and things like slurry from animal farms. This is all classed as sewage, and so the range of organic matter that it might contain is quite varied, and so there are a number of different processes that need to be carried out to make this safe to enter our regular water system. And so the first step is that we need to remove the solids from this water. So this might be twigs, or it might be leaves, or it could be anything like baby wipes or something like that. And so this process is called screening. And effectively, we use a gigantic wire mesh or a range of different meshes, and that filters out these large solids. But the name of the process is screening. And then after that, the wastewater enters a new tank, and there it is left to stand. And so that means it's not flowing, it's just in this big tank. And during this stage, sedimentation occurs. And that's where the more solid aspects of the wastewater sink to the bottom. They separate out from the liquid part of the sewage water, and we get this settling of the solids at the bottom. And this is sedimentation. The bottom is sometimes referred to as the solid, the sediment that has fallen to the bottom. And so by this stage, what we've got is we've removed the biggest bits, we've allowed the small particles of the solid to settle, and so the final stages of purification are using bacteria to treat these two parts of our separated mixture. And so the solid that is at the bottom of the tank is treated with bacteria that digest the waste anaerobically. And so this means that it is the absence of oxygen. That's what anaerobic means. And so these bacteria thrive when they're digesting the organic matter anaerobically. And that's the solid waste from the bottom. The liquid waste is referred to as effluent. And this is also digested by bacteria that it's been treated with. But what they do is they bubble oxygen through this liquid. And so these bacteria digest this effluent aerobically. And so we've got two types of digestion occurring when we're treating this with bacteria. The aerobic digestion is in the liquid, called the effluent, and anaerobic digestion occurs in the solid that is in the bottom of this sedimentation tank. And then having finished this process off, the sludge is now much kind of safer. We get some added benefits as well from this digestion because the sludge can be converted into methane gas. And we can also use the leftover sludge as fertilizer. So we're taking something that is very literally waste and we're making it into two useful products, one that's a fuel and another that helps our plants to grow. And then the liquid effluent is released into the rivers where it will enter the river system, and ultimately if it's going to be entering our homes, it will go through the stages that all water goes through of purification by filtration and sterilisation. Seawater and groundwater are treated to make them potable, and the table below shows information about the composition and treatment of seawater and groundwater. And you can see we've got seawater for this column, groundwater here, and there's the concentration of sodium ions and chloride ions before the first process, and then the concentration of sodium ions and chloride ions after that first process. We're told that seawater is desalinated during process 1, and we've been asked which pair of concentrations could represent X in the table above. And we've got various combinations of 0.003 and 0.5. Well, process 1 is reverse osmosis, and this, we're told, is desalination. That means simply the removal of salt. And we need to know that salt has the chemical name of sodium chloride, and that has the formula of NaCl. And so if we're removing salt, we're removing sodium chloride. And if we're removing sodium chloride, that means the sodium ion content and the chloride ion content are both going to go down. And at the beginning, the sodium and the chloride ion content is 0.5 moles per cubic decimeter. So both of these need to decrease in order for desalination to have happened. We can't remove one ion without the other during desalination. And so, in fact, the first answer is the correct answer. 0.003 is the only option where both of those concentrations has gone down. The sodium has gone down here, but not the chloride. And this time the chloride's gone down, but not the sodium. And actually the last one, neither of them has gone down. And so desalination is the first row. And then we've been asked to explain why the concentrations of sodium ions and chloride ions in the groundwater are unchanged by process 1. And so process 1 this time for the groundwater is filtration. And during filtration, the water is passed through a filter. And what a filter is a series of holes that will allow particles through, provided they are small enough to pass through the filter. And when you are filtering something that is dissolved, the ions are very, very, very small, and so the ions are small enough to pass through the tiny holes in the filter. And that's because they are dissolved in the solution, or you could just say that they are in the solution. And so filtering or filtration only removes solids that are insoluble, not the solutes that have dissolved in the water. And then for part D, we're asked to explain why the groundwater in the table above requires process 2 before the water is safe to drink. Well, process 2 for groundwater is the exposure to ultraviolet light. And actually that's fulfilling the same purpose as adding ozone to the seawater. Both of these are done to sterilize the water, and that means to destroy the microbes that are in the water, the microorganisms. And so we need to eliminate these microbes because they are harmful to our health, or we could simply say that they are pathogens, because by definition, a pathogen is a microorganism that can cause harm. And so to get both of these marks here, we need to say something like the water needs to be sterilized, or what that process involves, which is killing or destroying the microbes. And then the second mark is for saying the consequence of not doing that would be that these microbes would cause harm. After treatment, the groundwater in the table above is sold by a company as pure water. The groundwater in the above table is not chemically pure because the water contains sodium ions and chloride ions. And we can see that here. They're there after process 1 in very, very low concentrations, and exposure to ultraviolet light will kill those microbes, but it won't do anything to the sodium or the chloride ions. And so we've been asked to suggest what the company means then by pure. And what they mean then is that it is in its natural state, or it only contains natural substances that are always found in water, or that in its unadulterated state. We could also approach this from a separate angle, and we can say that it's not been contaminated or that there has been nothing added to the water. But the best answer is pure means it is in its natural state. And then we're told that chlorine is also used to treat some groundwater. That's to sterilise it. That's another mechanism for destroying those microbes. And we've been asked to describe the test for chlorine gas and give the result. There's 2 marks here. There'll be 1 mark for each. The test for chlorine gas is to use damp litmus paper. And it's really important that it is damp litmus paper. And what the chlorine does is it turns this paper white, or we could say it bleaches the paper. And this makes sense because actually chlorine that has been dissolved in water is one of the components of bleach. And so saying that the chlorine is bleaching the litmus paper is very literal. But that's why the paper needs to be damp, because without it, the chlorine would not dissolve in the water and would not interact with the paper. Sometimes for chemical tests like this, you cannot get the mark for the result unless you get the test correct. I think if you said litmus paper rather than damp litmus paper, this would be an exception. You would be able to get that 2nd mark, but you would not get the first one unless you said damp litmus paper. This question is about the chemistry of the Earth's atmosphere. The figure below shows how the percentages of gases in the Earth's atmosphere have changed since the Earth's atmosphere was formed. And you can see that we've got a graph here. On the x-axis, we've got millions of years ago, and it goes 4.5 billion years ago, in fact, at the origin. And then we've got the percentage of gases in the atmosphere at that time. And as we work our way to the right, we're getting closer and closer to present day, which is the time 0. This is how long ago, so this is present day. And you can see that we've got 3 gases on the graph. We've got carbon dioxide, which is the dotted line, so this line. We've got nitrogen, which is the dashed line, so here. And oxygen is the solid line. And we've been asked to explain the change in the percentage of gas in the region labelled A on the figure, on the graph. And so when you're asked to explain, that means give a simple description and then give the reason for it. So make a point and then explain that point. And so we need to find the region labelled A, and inside that region labelled A, we've got the dashed line, so that means we're talking about nitrogen. And so in terms of an explanation, the change first and foremost is, well, this value is going up. So the percentage of nitrogen was increasing. Don't get bogged down by actually quoting values. Just simply say the percentage was increasing. And the reason that the nitrogen levels went up is that nitrogen was produced when volcanoes erupt. So we would say volcanic activity, or it was released when volcanoes erupted, or something like that. So 1 mark for the fact that the nitrogen increased, and another mark for linking it to the fact that it was caused by volcanic activity. And then we've been asked to explain the change in the percentage of gas in the region labelled B on the graph. And so B is the dotted line, which means it's to do with carbon dioxide. This time it's starting high and it is going down. And so we will get 1 mark for saying that the carbon dioxide is decreasing. So like in the previous question, we need to personalise it to the gas that this is representing, but that's just a case of using the key correctly, and we need to say what the trend is. So the carbon dioxide is decreasing. And then for our deeper explanation, we're giving a reason why this CO2, with this carbon dioxide, is going down. And there are a number of reasons why it's going down, but we need to be careful because this is more than 4 billion years ago. And so we need to steer clear of photosynthesis. That was the most common wrong answer on this paper, because photosynthesis hadn't happened until much more recently than that. So the reasons why the CO2 decreased is that carbon dioxide dissolved in the oceans that formed when the Earth cooled down. So the Earth Earth cooled down, and that meant that the water vapour condensed to make the oceans, and then carbon dioxide dissolved in those oceans. And then that continued to happen, and also the formation of carbonate precipitates or sediment or limestone or carbonate rocks, all of those things kind of fall together once there's an ocean and that there are carbonates in the ocean. So again, the first mark is for simply stating the trend that the carbon dioxide is going down, and the second mark is for saying one of the reasons why it's going down. We don't need to give lots of reasons, just one of them is fine, because we're developing our first statement of the decrease in carbon dioxide. Next, we're asked to compare the changes in the percentages of the gases in the region labelled C in the figure above. So this is just a little bit less than 1.5 billion years ago. And so when you're asked to do a comparison, you need to say whether things are the same or whether they're different, and if they're different, which one's bigger, which one's increasing, which one's decreasing, etc. And so on this occasion, we're comparing the oxygen line, that's the solid line, to the carbon dioxide line, which is the dotted line. And what we can see is that the oxygen line is going up as we get closer to present day, and the carbon dioxide line is going down the closer we get to present day. And both of those two clauses are essential for the first mark. The carbon dioxide is decreasing and the oxygen percentage is increasing. But that's not really a comparison yet. We have given a simple comparison, I suppose, but we've not gone deeply into that. But what we need to notice is the rate of increase in oxygen is the same as the rate of decrease in carbon dioxide. It almost looks like almost looks like an X that is perfectly symmetrical. And that's where the second mark is going to come in. The increase and the decrease are occurring at similar rates, or maybe you could also say the same rate. They're not going to double check this in terms of the precise language. We aren't expected to know exactly what the gradients are. So the increase and the decrease are similar in the same period of time. And then we're asked to say what the cause of these changes in the region labelled C is. And the cause of this change is photosynthesis. The trees and plants in the early Earth will be taking in that carbon dioxide and releasing oxygen. But you can simply get this from just saying photosynthesis. And this makes sense that it would be exactly equal and opposite, because if you consider the word equation for photosynthesis, we have got carbon dioxide and water turning into oxygen and glucose. And then if we turn this into the symbol equation, you can see that there are 6 CO2 being used and 6 oxygen being produced. So it's very logical when you see this that the use and production will be equal and opposite. So they're taking place at the same rate during the process of photosynthesis. Natural gas is a fossil fuel. Describe how deposits of natural gas were formed. Now, this is a bit of a sneaky question, actually, because you're meant to know how oil forms and how coal forms, but it never explicitly says how does natural gas form. However, it is a reasonable question for them to ask because natural gas forms in the exact same way and in the exact same place as crude oil. Now, as the name suggests, they are fossil fuels, which means they are formed from the remains of living organisms that have decayed in a way that is non-standard. Now, unlike coal, which is formed from the remains of plants, typically in swamps, oil and also natural gas are formed from the remains of marine organisms. And so that's the angle that we need to take for this question. So millions of years ago, plankton, which are tiny microscopic marine organisms, they were living in the oceans. You could also say algae for this marking point. And then they died, as all organisms do, and they sank to the bottom of the ocean. And once they were there, they were covered in sediments. Now, sediments is a catch-all word that is used to describe mud and sand and bits of rock and things like that. And the idea there is that the marine organisms are being buried under this sediment. So that's the second marking point that you need to include. You could also say that as a consequence of this being buried by the sediment, the oxygen that typically supports the decomposition of something once it's died is being blocked from the remains of the plankton. And so what that means is the plankton is going to decay in anaerobic conditions, in other words, in the absence of oxygen. And that's the reason why we don't get normal decomposition and we get the formation of fossil fuels instead. In addition to denying oxygen to the remains of the plankton, we also have this layer upon layer of rock forming at the bottom of the ocean, and that subjects the remains to extremely high pressure. You could probably refer to it more simply as compression, but high pressure is better. And in addition to that, it also causes the remains to be subjected to really, really high temperatures as well. To get the third marking point, you do actually need to include a reference to the high temperature and the high pressure as well, not just one of them. And to complete the formation of the fossil fuels, really we should acknowledge that this is not a quick process such as the decay of an organism normally is. It will take place over millions and millions of years, and that's why we refer to it as a fossil fuel and why we refer to fossil fuels as being non-renewable, because it takes such a long time for them to form in the first place. We can't possibly replace or replenish them at the rate that we can use them because it takes millions of years. Ammonia is produced in the Haber process. The raw materials for the Haber process are nitrogen and hydrogen, and the equation for the reaction is shown here. We can see the nitrogen, N2, diatomic gas, and hydrogen, H2, also a diatomic gas. They are the reactants. It's a reversible reaction, and we're producing the ammonia gas, which is the main point of the Haber process. We've been asked to give the sources of the nitrogen and the hydrogen used in the Haber process. Well, the nitrogen comes from the air. Around about 78% of the air that we breathe is made of nitrogen, and so that nitrogen is extracted from the air by a process called liquefaction. And so simply for the 1 mark here, we can just say air or the atmosphere. The hydrogen comes from natural gas. Natural gas forms in pockets, typically above where we get crude oil formation as well. So the major gas in natural gas is actually methane, so it's totally fine to say methane as an alternative of natural gas. There is in fact very, very small amounts of ethane and propane and butane as well mixed in together, which is why it's called natural gas or natural gases. The chemical reaction that you use to get the hydrogen out of the methane is a reaction with steam, and therefore it is actually also okay to refer to the raw material used to get the hydrogen as water or steam as well, because that is one of the 2 components in the chemical reaction that gets the hydrogen out of the methane gas. But the primary answer that I suggest you remember is that the hydrogen comes from natural gas. And then the question says, how does the equation for the reaction show that the atom economy for the forward reaction is 100%? Atom economy, usually expressed as a percentage, is a measure of how efficient a chemical reaction is. And this efficiency is based on the mass of the atoms that we've paid our money for at the beginning, so the nitrogen and the hydrogen in this case, and the conversion of those atoms into useful products, the ammonia. Now, because there is only one product, the ammonia, and that's the one that we're trying to make, there is 100% atom economy, as the question is telling us, because we only make one product. And a different way of flipping that is saying that there was no other product being formed at all. And if there's no other product being formed at all, then that means that there is no waste product being formed, and so we are being 100% efficient. All of the atoms that we've spent our money on are being converted into the desired product. And so there is only one product, That's all you need to say to get this 1 mark. Figure 1 represents the Haber process, and you can see that the nitrogen and the hydrogen raw materials are put into a reactor, where there's an ion catalyst, by the way, and this is where the Haber process reaction occurs. And then because this reaction is reversible, that means we don't get 100% conversion into the ammonia. And so what comes out of the reactor is the ammonia, of course, but additionally the unreacted nitrogen and hydrogen enters this container X. And then from this container X, the ammonia is removed, which is what we want. That's what we're going to use to make fertilizers, etc. But then the unreacted nitrogen and hydrogen get pumped back around into the reactor. It gets recycled. And this question here is asking us how that process occurs. Explain how the ammonia produced is separated from the unreacted nitrogen and hydrogen in X. The process occurring in X works because we've got 3 gases that have all got different boiling points. And when we cool these gases down, the one that has the highest boiling point is the one that is going to condense. And ammonia has the highest boiling point out of all 3 of these gases. And so when we drop the temperature down from around 450 degrees C that it was in the reactor, we keep lowering it and lowering it and lowering it. And once the boiling point of ammonia is reached, the temperature is not high enough to keep that ammonia as a gas anymore. And so the ammonia turns into a liquid. The hydrogen and the nitrogen, they have a boiling point much lower still, and so it is still hot enough to keep those 2 molecules as gases, and so they remain as gases, but the ammonia has been liquefied as a result of this cooling down. And what that allows us to do is to get liquid ammonia out of the bottom of container X, and then the gases of nitrogen and hydrogen, they remain in X, and then they can be pumped around still as gases back into the reactor, where they will go again and react again to make more ammonia. So for 2 marks, we need to get 1 mark for saying that they cool it down. You could probably say that the temperature is decreased for this same marking point, and then the second mark is for saying that the ammonia liquefies, or it condenses, or it turns from a gas into a liquid. The Haber process uses a temperature of 450 degrees C and a pressure of 200 atmospheres. The table below shows how the percentage yield of ammonia produced at 450 degrees C changes when we use different pressures. And we've been commanded to complete figure 2, which is this graph on the right hand side. The first 2 points have been plotted for us, and we need to use a suitable scale on the x-axis, so that is this x-axis here, where they've already labelled it as pressure for us, and then plot the remaining data points and add a line of best fit. So our first job, before we can plot any points, is to work out what a suitable scale is. Now, ordinarily, if we're asked to do this, we might have to completely work this out for ourselves, and we need to be guided by the fact that our scale needs to take up at least half of the graph paper that we've been given, and our plotted points also need to take up half of the space that there is. Those are really important guiding principles. But here, because they've plotted the first 2 points for us, we can kind of work backwards to work out what the scale must be. So the percentage of ammonia being 9, that's this point that they've plotted here, and that's 60 atmospheres for this point, like so. And that means that this point must be 60, and the next one along is 18, and the atmospheres is 120, so that means this is 120. And so what we can deduce here is that if this is 120, this point here must be 100. And so each minor grid line is 10 atmospheres. And so that means we've got 50, 100, 150, etc. as we work our way along to the right-hand side. So that's 1 mark now for a suitable scale. And then it comes to just plotting the points on the graph. The next one that hasn't been plotted is 180 atmospheres. So here's 150, 3 small squares along makes us 180, and then we need to go up to 25, and so we're plotting it here. The next one is 240, so that's 250, so 240 is 10 less than that. and we need to work our way up to 30. Now, we haven't explored this yet, but 30 and 31, each small line is 1%. So that's quite a nice scale, really, that they've given us for this graph. So 31 is going to be here. And then 300, well, that actually is on a major grid line, so that's going to be here. And we're going up to 36, so this is 35, and so here will be 36. 360, well, that's 350, 360 is here, and we need to go up to 40, so that again is on a major grid line. And then 420 is the last one, and so we need to look for 400 and 410, 420 is here, and we're going up to 40, 41, 42, 43, and so that is our final point. There are 2 marks for plotting these points, and how this normally works is if you've got 5 points that we need to plot, like we have here, you'll get 1 mark for plotting 3 or 4 of those points correctly, and you'll get the second mark if you've actually plotted all 5 of them correctly. How much tolerance will they allow? Well, you can normally get within half a small square of where it should be. And so that means that if you were plotting a point at 31 and you plotted it at 31.5, you would probably get the benefit of the doubt in that case. But if you were plotting 31 and you plotted 32, you would lose that mark. So as a rule of thumb, plus or minus half a small square is what we're working towards for either of those axes. And so because that is the case, it's important to make sure your points are nice and clear. Don't draw with quite a chunky pencil so that it's not really very obvious where the line is. And so, for instance, this cross here is probably too big, and so that's why I've gone for quite small crosses early on. So it's very obvious which area of the graph paper I'm actually targeting with my cross. Crosses are definitely better than dots because it's easier to aim them, and it's also easier to see them once we draw our best fit line that we're about to draw in a minute. It's very easy for dots to get hidden by a best fit line, and so you could end up losing the marks for plotting the points if your best fit line covers up those dots that you are using to indicate the points. Sometimes it's really important to plot the 0, 0 mark here, but we haven't been given it, so you should ignore that on this occasion. But just be on the lookout if at the top of the graph they were saying 0 atmospheres was 0% yield. We've not been told to plot that point, so there wouldn't be a mark for it, so let's not worry about it. And then it comes on to the best fit line. When you draw a best fit line, it's again really important that you would have a sharp pencil to draw this so that the best fit line does not cover up the points that you have plotted. And again, there is a plus or minus half a small square for where your best fit line should be. So again, you haven't got much of a margin for error, so don't use a blunt pencil to do this. It's also really important that your best fit line is a single line and you don't lift the pencil off the paper whilst you're doing your best fit line. That's a really crucial idea, because if you do lift your pencil off the paper, the line could end up looking feathered, which means it's kind of a zigzaggy line. We absolutely in chemistry never do point-to-point best fit lines, and as I've already said, we don't want those lines to be thick. So this needs to be a curve, and you can sort of tell it's a curve if you get your head down towards the paper. Never pick up your test paper in a test because it might look like you're showing somebody your answers. But if you get your head down near the paper, you can see it starts to curve pretty early on. It's definitely not a straight line, and I can show that with a straight line like this. You can absolutely see that the straight line obviously continues in a linear direction, but these last few points bend away. Now, clearly I wouldn't recommend drawing a straight line just to find out whether it's a straight line, but you can pick up your ruler and kind of turn it onto its side and look down at your paper, and you can see that you end up with some points curving away from the best fit line. So a straight line is not appropriate. It needs to, on this occasion, be a smooth curve like I'm drawing here. And there would be, as I've already said, a little bit of a margin for error, but we need to draw a smooth line that is not feathered and is not too thick. And then we're told to determine the percentage yield of ammonia at 450 degrees C and 500 atmospheres, and show your working on figure 2, which is the graph that we've just drawn. And so the significance of it being 450 degrees C is basically giving us permission to use the graph that we've just drawn, because that was the temperature for all of this data. But 500 atmospheres is a pressure that was not measured, so we don't actually know what the percentage yield is, but we're using our graph to work out what it probably is. And so when they've said show you're working on figure 2, that means that there is a mark here for indicating on our graph how we are getting towards our answer. And the way that we would do this is by a process referred to as extrapolation. Extrapolation is where we look at a set of data, for instance, the data that we've got here, and we look at the pattern that it is showing. And then when we get to the end of the data that we've collected, we assume that this pattern will continue in the sort of direction that it was going. And so that's the process of extrapolation, to continue a pattern and assume that it does continue in the same way. And so there'll be 1 mark in this question for literally drawing a continuation of that line. Now that could be in the exact same way that we did before, or it could be a dotted line or a dashed line. Either of those is absolutely fine. But what is really important is that we continue our line to at least 500 atmospheres. If you go beyond, that's absolutely fine, but it must go to at least 500 atmospheres as I'm showing here. And then having done that, what we're doing is we're looking at our 500 atmosphere line, and we're looking at the percentage that we reach. So my line went to about 46%, perhaps just a tiny bit under, but we'll get a mark here for reading across to our y-axis to wherever our extrapolated line gets to. So mine got to 46%, and so to correctly read it, I would have to write 46% as the percentage yield at 500 atmospheres. Now, if you extrapolated your line badly and you got a different number, you would get some credit for correctly reading off your poorly extrapolated line. And depending on how you plotted your points earlier, this will also affect your best fit line, which will affect your extrapolation, which will affect your percentage. So as a result of this, there's probably going to be a range of acceptable answers, perhaps between 45 and 47, or maybe even beyond, depending on the quality of the line that you drew earlier. The equation for the production of ammonia in the Haber process is shown here. We've got nitrogen reacting with hydrogen, and then we're shown that this is a reversible reaction and we're producing ammonia. We're told that the forward reaction is exothermic. The conditions are a temperature of 450 degrees C, a pressure of 200 atmospheres, and the presence of the iron catalyst. We've been asked to explain why these conditions, those ones mentioned above, are chosen for economical production of ammonia in the Haber process. You should include references to the rate of reaction and the position of equilibrium. When you're asked a question like this, it's really important to make sure you know what the question is asking you to do. We have to mention all 3 of these conditions. We have to talk about both the rate of reaction and the position of equilibrium, and we've been told that we're looking for economical production of ammonia, which means we also need to mention cost. As is really common with equilibria and Le Chatelier's principle related questions, it's also a good idea to have the idea of compromise in mind to support what we're saying. That's a lot of things to keep track of when you're answering this question. So I recommend that you sketch some kind of table a little bit like this, and it can always look like this, with the conditions down the left-hand side and then the features of the reaction along the top. And then you can just tick off once you've mentioned how one of these conditions affects the feature that you're discussing in your answer, and you can make sure that you don't miss anything out. It's worth noting that the command word in this question was to explain, and that means that we need to develop our ideas and not just make a simple statement about something. So my advice when you're answering this question as well is to take one condition at a time. So I'm going to tackle everything to do with temperature that I can think of. So first of all, we need to state that a higher temperature will give a higher rate of reaction because there will be more frequent successful collisions. I really recommend using comparative language in evaluation type questions like this. And then we need to move on to talk about equilibrium. A higher temperature is going to shift the position of equilibrium to the left-hand side. And we can tell that that's the case because the forward reaction is exothermic. And what's gone unspoken here is that therefore the reverse reaction will be endothermic. So if we raise the temperature, equilibrium is going to shift in the endothermic direction, which is left. And then in terms of a compromise then, we're talking about this being a compromise between the rate of reaction and the position of equilibrium. Additionally, if we're trying to reach higher temperatures, that will use more energy, and so therefore that will increase costs. And so you could also say that the temperature that we choose is a compromise between the rate of reaction and cost. So we've said more than enough about temperature there. Let's move on to pressure. A higher pressure will give a higher rate of reaction because there will be more frequent successful collisions. This is the same concept as the temperature. Now, the equilibrium position, though, will be the opposite, and that's because there are 4 molecules on the left-hand side of the equation, but only 2 on the right-hand side of the equation. So therefore, a higher pressure is going to shift the position of equilibrium to the right-hand side because there are more molecules on the left-hand side. And so it seems like a high pressure is great in terms of the rate of reaction and in terms of the equilibrium position and therefore the yield of ammonia that we produce. However, a higher pressure will require more energy and that will therefore increase the costs. And a higher pressure will also require a stronger reaction vessel in order to withstand that high pressure, so that will increase the costs as well. And so the compromise on this occasion for pressure is between the rate and the yield, both being high, without setting the costs being too high. And so it's a compromise between rate and cost. And then if we consider the catalyst, we know that catalysts, when we use them, we get a higher rate of reaction because the activation energy is lowered. And that's by providing an alternative reaction pathway. And so because of that, this will mean that we will be reducing energy costs potentially because we don't need to use such high temperatures to get a fast rate of reaction. And then in terms of equilibrium, when we use a catalyst, this has no effect on the position of equilibrium because a catalyst will lower the activation energy of the forward reaction and the reverse reaction precisely the same amount, and so we're not going to affect the position of equilibrium by employing a catalyst. At most, we might affect the speed at which we reach that position of equilibrium, not what the position actually is. And so you can see here I've made quite a few separate points that I've marked as bullet points. I've absolutely hit every condition and I've hit every aspect of every condition. In reality, you probably wouldn't need to say all of these bullet points to get all 6 of those marks. What I would say is that you need to mention the temperature and the pressure and the catalyst. You need to mention the rate and the equilibrium and the cost, and I would recommend compromise as well. And you probably don't need to have a tick in every single row for temperature and pressure and catalyst. You just need to make sure you've got ticks in each row and ticks in each column, and absolutely that you've mentioned cost because they've asked us about the economic production of ammonia. This question is about the reaction between sodium thiosulfate solution and hydrochloric acid. When hydrochloric acid is added to sodium thiosulfate solution, the mixture gradually becomes cloudy. And you might recognise the names of those chemicals. These are the chemicals that you mix together in the disappearing cross experiment. You mix them together, you start the timer, and gradually a cross, which is placed underneath the conical flask, is no longer visible to the observer looking down through the contents of the flask. The equation for the reaction is shown here. We've got sodium thiosulfate on the left-hand side reacting with hydrochloric acid, making sodium chloride, water, sulfur dioxide, and sulfur. And we've been given the state symbols for each of them. Sulfur is produced in the reaction. Why does this mixture become cloudy? Well, they've told us about the sulfur, and sulfur has got a little S in brackets after it. These are the state symbols for all of the chemicals in the reaction, and the state symbol S means solid. And so that means that the sulfur has been produced as a solid or as a precipitate or insoluble substance. And it's actually the presence of that creamy coloured sulfur that obscures the cross from underneath the container because the sulfur is opaque and we can't see through it. The other state symbols, by the way, liquid water, sulfur dioxide is a gas, and then the other three chemicals are aqueous, which means they are dissolved in water. And then we're shown a diagram for how they're setting up this experiment. It's a bit different to the normal disappearing cross experiment. We're told that the student investigated the effect of changing the concentration of sodium thiosulfate on the rate of the reaction. That's similar to the disappearing cross experiment and how it can be used. And we're shown a diagram for the apparatus. There is a light source shining light through the reaction mixture, and then there is a light sensor, the other side, detecting the percentage of light that gets through. And we're told that a smaller percentage of light from the light source reaches the light sensor as the mixture becomes more cloudy. And here is the method that they used. They added 50 cm cubed of 0.1 moles per decimeter cubed sodium thiosulfate solution in the beaker. That's the concentration, that's the volume. And we add 10 cm cubed of hydrochloric acid to the sodium thiosulfate solution, immediately start the timer, record the percentage of light from the light source that reaches the light sensor every 20 seconds for 120 seconds. And then repeat steps 1 to 4 using 0.2 moles per decimeter cubed sodium thiosulfate solution. So double the concentration. And so in a sense, this is exactly like the disappearing cross. You change the concentration, you change the temperature, and you see the rate at which that cross becomes obscured. The difference this time is as time passes, the percentage of light reaching the sensor decreases. But it doesn't decrease at the same rate, at a constant rate. It decreases steeply at first, and then it decreases a little bit less, and then a little bit less, and then it levels out. It stops decreasing, and we can assume that the reaction is over. And then we're told that the percentage of light reaching the light sensor decreases by 1% when 7.1 times 10 to the minus 5 moles of sulfur is produced. And we've been commanded to determine the rate of reaction in moles per second for the production of sulfur at 30 seconds. And we're told that we should draw a tangent on figure 2. When you calculate the rate of any reaction, you're always going to be doing the change in some quantity divided by time. That might be centimetres cubed of gas per second or mass of gas per second. On this occasion, we're going to be working out moles per second. And so from the graph, you can see that we've got percentage on the y-axis, not moles, but we do have seconds on the x-axis. In some cases, we're asked to work out the average rate of reaction, and that would be for a change in percentage divided by time. We've been asked for the rate at 30 seconds, and that means that we need to draw a tangent, and they've prompted us that we need to do so here. So you do this by finding 30 seconds on the x-axis, going up to the curve at that point, and then drawing a tangent at that point. Now, tangents are straight lines. This graph is not straight line, this is a curve graph. But if we draw a straight line at 30 seconds, we can match the gradient of the graph at that time, but then the graph will curve, but our gradient will continue in a straight line. When you draw a tangent, my strong recommendation is that you always, if you can, extend the tangent to the two axes that we've been given, because that will make the use of that tangent much easier. And so you can see here I've drawn my tangent. It meets the curve at 30 seconds, but it continues in a straight line all the way to the x-axis and all the way back to the y-axis. And so now we've got our tangent, we need to work out the gradient of this tangent. And so on the y-axis, the value starts one line above 70, and each square is worth 2%. So it starts at 72%, and it goes all the way down to 0%. That's why I suggest you continue the tangent to the axes where possible, because that means our change in y is 72%. And the x-axis, well, it starts at 0 on the x-axis, and it goes all the way along to 3 little squares past 70, and each little square is again worth 2, so it's gone to 76. So our change in x is 76. So our tangent is 72, the change in y, divided by 76, the change in x, and that gets us 0.947. Now, this value is the percentage of light per second, because I've divided percentage by seconds. But we've been asked to work out moles per second. And so that means that we need to convert percentage per second into moles per second by converting percentage into moles. Now, in the question, we were told that a change of 1% means that 7.1 times 10 to the minus 5 moles of sulfur has been produced. Now, our percentage hasn't quite changed that much. It's changed by just less than 1%. And so the moles of sulfur produced in that time will be just less than 7.1 times 10 to the minus 5. And we can actually calculate its value by taking that number of 0.947 and multiplying it by 7.1 times 10 to the minus 5. And then when we get that, we can get a value of 6.73 times 10 to the minus 5 moles per second. And then we're asked to explain why the rate of reaction changes between 0 and 60 seconds, and answer in terms of concentration. Well, at the beginning of any reaction, the reactant particles will be in the highest concentration they will ever be during the reaction. When over time these particles collide with each other, they will get used up in this reaction, and so the concentration of the reactants is going to decrease, and therefore the frequency of successful collisions will also decrease, and so the rate of reaction will slow down. And we do need to say that the rate of reaction will slow down because all they've asked us to do is explain why it changes. And so in a situation like this, we need to say what the change is. And you can tell that this is the case from the graph. The gradient is steepest at the beginning, which means that the rate of reaction is greatest at the beginning because those concentrations of the reactant are greatest. And then over time, the gradient decreases as that reactant concentration decreases, and the concentration decreases some more, and the gradient decreases some more, and so the rate of reaction decreases as time passes. The graph that we've been looking at shows the results for when the concentration of sodium thiosulfate was 0.10 moles per decimeter cubed concentration, and we're told that the sodium thiosulfate solution was in excess in the investigation. Then we're told that the line of best fit on this figure is horizontal between 80 and 120 seconds because the reaction stopped, and we're asked to explain why the reaction stopped. Well, when you've got a reaction between any two chemicals, one of them is likely to be present in a higher quantity than the other, and that is what being in excess means. That means we've got more than enough of it, and it will not get used up in the reaction. And the other chemical is the limiting reactant, and that is the one that will get used up. And so if the sodium thiosulfate solution is in excess, then it's the hydrochloric acid, the other reactant, that is going to be used up. And if the hydrochloric acid is being used up, its concentration is going to go down to 0, and therefore the successful collision frequency is going to drop to 0. There will be 0 successful collisions per second. And then we're asked to sketch a line on figure 3 to show the results that you would predict for 0.20 moles per decimeter cubed sodium thiosulfate solution. So, in other words, double the concentration of sodium thiosulfate. Well, there's 2 marks for this, and for a situation like this, which is a really common question, there will be 1 mark for the gradient of the line that you draw and another mark for the finishing height that this reaction will curve and then flatten out at. And the gradient is determined by how fast this reaction is. So let's look at that first. If the concentration is twice as big, the frequency of successful collisions will be twice the number, and therefore the gradient will be twice as steep because the rate of reaction will be twice as fast. Now, for a question like this, they don't need the gradient to be precisely twice as steep. They actually just need it to start at the same place and to be steeper than the original line. And then we need to think about how much we're going to end up dropping that percentage to in the end. Well, all we're changing is the concentration of sodium thiosulfate, and sodium thiosulfate is already present in excess, so adding more of it is not actually going to reduce the percentage by any more than the original experiment did, because that hydrochloric acid is still going to be used up, and it's the hydrochloric acid that determines how much sulfur we produce, so how much cloudiness there is. And so all that will happen is that hydrochloric acid will end up getting used up faster, but we're going to flatten our line out at the same position. It still needs to finish at 24%. It needs to level off at 24% and be steeper than the original line. 1 mark for each of those features. The student did the experiment again the next day, and they found that the same method produced different results for the percentage of light reaching the sensor. How could the student improve the method so that the same percentages of light reach the light sensor? That means the same percentages on those 2 days that they did the experiment on. So we've got the option of recording the percentage of light every 10 seconds. That's not the right answer. That will just give us a better idea about how our curve curves as time goes on. So it will improve the experiment, but not in the way that we're being asked to do here. Stop light from other sources reaching the light sensor. That's the correct answer, because if it's a sunnier day, there might be more ambient light. That means there might be more light coming in through the windows and interfering with this experiment, and light from outside might be reaching this sensor and elevating the percentage of light greater than it should have been and greater than it would have been on a cloudy day. If we use a larger volume of sodium thiosulfate, that would just increase the volume here, and that wouldn't affect the light getting through. And then we could also say that using a more sensitive light sensor, assuming that we use the more sensitive light sensor on both days, that's not going to make any difference. It's the changes from one day to the next that is going to affect these variations. The students improved the method so that similar results were obtained on different days. What name is given to similar results obtained on different days under the same conditions by the same student? We're ticking 1 box here for 1 mark. Anomalous, that's not the right answer. An anomalous result means an odd result that doesn't fit in with the expected pattern, and that could be for a number of reasons. Precise, no, that's how close our values are together. And so that means that maybe we did the same thing multiple times and we got the same number each time. Repeatable is the correct answer. Repeatable means literally the same person did the same experiment and got the same results each time. Reproducible, that's if a different person repeated the experiment and got the same results on different occasions. And so reproducible and repeatable, they're really similar. Repeatable is for the same person doing it multiple times. Reproducible is more than one person doing the same thing and getting the same results. And then we're shown a new graph which has got the volume of the 2 different reactants in this experiment on the x-axis and the mass of sulfur that has been produced on the y-axis. And this dashed line, that is for sodium thiosulfate as per the key, and then the solid line, that is for the hydrochloric acid. And we're being asked which expression from the options below shows the relationship between the volume of sodium thiosulfate solution, so the dashed line, and the mass of sulfur produced, and that is the y-axis. And so as the volume of sodium thiosulfate increases, that's this line here, you can see that the value on the y-axis also increases. And it doesn't just increase, it's actually directly proportional because it's a straight line that goes from the origins, from 0, 0. And that means that the first answer is the correct answer. The volume is directly proportional to the mass produced. And our final question is to determine the simplest whole number ratio of the volumes of sodium thiosulfate to hydrochloric acid, which completely react with each other. That's really important. The fact that they completely react with each other means that they will be producing a specific mass of sulfur in grams. Now, actually, it doesn't matter what mass of sulfur you choose to produce. It just matters that you are producing a specific amount. And so really, you could use any mass you like, and you would just need to read across and find out what volume of sodium thiosulfate was required to make that mass, and what volume of hydrochloric acid was required to make that particular mass of sulfur. And so the trick here, I think, is to find a place where, when you read across, you meet a minor grid line at the point that the line crosses it. So for instance here, at 0.35 grams of sulfur being produced, when we read across, we find out that the sodium thiosulfate is on this minor grid line here, one little square past 100, so that means 110 cm cubed of sodium thiosulfate was required to make 0.35 grams of sulfur. And if we continue reading along this line further, we get to a point on the hydrochloric acid line that is also on a minor grid line. That is one small square before 450. And so that means 440 cm cubed of hydrochloric acid was required to make that particular mass of sulfur. And so you'll get your first mark of the 3 for choosing a point on your graph that you can use readily and for marking on it. It's really important to annotate your graph to show that you are using figure 4 as the question demands that you do. And then we have to turn this volume ratio into the simplest whole number ratio. And when you're simplifying a ratio, you might be able to do this by inspection, but you can't rely on that. And so the strategy I suggest you employ is to divide both of the numbers by the smallest of the two. And the smallest of the two here is 110. So 110 divided by 110 is, of course, 1. 440 divided by 110 is 4. And so therefore, the simplest whole number ratio is 1 to 4.